continued. Particle kinematics and kinetics. In rotating coordinate systems. And we did the thing with polar coordinates last time. So now, we're going to talk about one simple motion riding another simple motion. Yeah. So, for example, if you're tracking the motion of this particle P, and this disk is rotating at the same time that this arm is in circular motion, then if this arm wasn't rotating, if this was fixed, calculating the motion of this particle would be really easy. That's just a circular motion, right? So that would be a simple thing to calculate. And if this disk was fixed and the arm was rotating, it would be easier to calculate the motion of that particle because that's just a different circular motion. But the two of those together with the tools we have so far is really complicated. Okay. And so we're going to always think of one of these motions as the horse and one of these motions as the cowboy. Yeah.
So we could take this to any other engineer and they would know.
They probably just forgot. So, and there's no wiggle room on which one is riding the other one. And what we're looking for is how do you choose? Okay. How do you know which is which? Well, really, it's just a matter of imagine each motion is fixed. Is the remaining motion easy to calculate? Most of the time, probably, at least a lot of the time, these two simple motions are going to be circular motions. I guess they could be spherical too. Well, let's say circular. So the axis of rotation of the cowboy, the rider, depends on the motion of the horse. Okay, so let's think about this example. So first, I've already labeled these. The disc motion is riding the motion of that bar. But let's imagine that it was the other way and just see, what happens. So imagine that, well, forget about that for a second. Think about the second one. These are both circular motions. So as this disc rotates, does it change the axis of rotation of the bar? That's the question. No matter what's happening, that the bar's axis of rotation is in the, straight up. I guess straight down to the right hand wall. But now think of it the way that we know it actually happens. Does the axis of rotation of this disc change as the bar rotates around? It does. At this point that's shown, the axis of rotation is this way. Once that bar swings around here, the axis of rotation will be this way. Okay? And so if you can find that relationship, then you know that, it's easy to figure out which is the one that's sort of the base of the motion of the second one. Okay? I'm going to call it the horse and the cowboy.
So how is these?
You can do it with a hat.
How is the speed of the horse in relation to the force of the motion of the cowboy? Like if we spin it fast enough, is the force of the horse going to change?
Yeah, the forces, they affect each other. But all we're thinking about now is which one of those motions affects the axis of rotation of the other motion. Whatever one affects the axis of rotation of the other is the horse. The one that's just along for the ride doesn't affect the axis of rotation of the other one is the cowboy. We're always going to choose right. Mm-hmm. Yeah, definitely in this case, that's true, yes. So always choose a coordinate system that's fixed to the horse. And the reason you do that is your coordinate system is in a simple motion, and then relative to the coordinate system, the other motion is simple. You basically put it in between those two simple motions, and you use the rules of rotating coordinate systems to calculate the true velocity and acceleration. All right, so let me do an example. So let's say we have a rotating shaft coming out of the wall, and it's attached to ET. No. That horse and cowboy thing is just a analogy. I guess, yeah, it's like a stirrup. It is like a stirrup. Okay, yes. So there's a wheel that's the axle of the wheel goes through those things. This wheel spins as this thing spins. So let's say that this is rotating at 20 radians per second. Oh, I guess that's how I said it before, but I guess I mean it to be just this head that's spinning around that shaft. And let's say that this disc is rotating this way with an angular velocity of 5 radians per second and an angular acceleration of 15 radians per second squared. This other rotation, that's just a constant angular velocity. And let's say that the point we want to calculate is this point P. We want to know what that point P is doing. The radius of this disc is 0.4 meters. And we want to calculate, well, let's get the velocity. .4 meters. We want to calculate the velocity of that point P and the acceleration of that point P. And then might as well say that, just to sort of be explicit about why we would normally want to calculate this stuff, say that there's a mass at P of 0.1 kilograms force acting on that mass. Okay, so there are two motions here, spinning around this way and the disc spinning around this way. Which of those two is the horse? The 20, yeah. So this motion is the horse. This one is the cowboy. And so we know that the coordinate system is going to be fixed to that the horse, the 20 radians per second motion. Okay. You have a few options of where to put the coordinate system, but to make this as simple as possible, I'm going to choose a coordinate system like this. So there's X, Y, and Z coming out of the page. And we know we're going to use the equation. So for A, we're going to use an equation that says the velocity of that point P is equal to the observed velocity of P plus the angular velocity of the coordinate system crossed with position vector. there's another way we could think of this too, if it's helpful. We could think of this as the time derivatives of the components of the position vector plus capital Omega cross P. And so we'll use whichever one of these two is more useful to us. Some problems it's one, some it's the other. And so now we just have to figure out the angular velocity of the coordinate system, the position vector that we're interested in, which one of these two we're going to use, and how to represent those. You can think of this velocity observed as the velocity of P if the horse were at rest. Okay, so which of these two in our problem is a more useful way to think about it? Is there any, I guess the question is there any use for taking time derivatives of the observed positions? No, I mean, that would be useful in the case that we have the position vector represented as a function of time. We don't. And so we're going to think of it this way. Then in that sense, yeah, what we're just imagining that this isn't spinning at all. There's no 20 radians per second. And we're just watching this point P. We're just sitting right here watching this point P go in circular motion around the origin. Okay. Yep, we're watching the astronaut. We're sitting fixed right here and watching P cowboy rotate around. And we're only concerned about this one point on the cowboy. Right. Okay, so the velocity of P that's observed, it's just a circular motion, so it's going to be equal to lowercase omega cross r. What's lowercase omega? Yeah, 5 radians per second in the negative z. So 0, 0, negative 5. And then what's the r vector? So the center of the circular motion is here. The point we care about is here. So we're going 0.4 meters in the negative y direction. So 0, negative 0.4, 0. And so the velocity of that point that's observed by the coordinate system is 0, 0, negative 5, crossed with 0, negative 0.4, 0, negative 2, 0, 0. Yep. Meters per second. Yep. So now we have this first term of the, this is the one that we're using. Now we have to come up with the angular velocity of our coordinate system and the position vector. So what's the angular velocity of the coordinate system? Yeah, that's negative 20 in the x direction, 0, 0. And then what's the position vector? Yeah, and it's the same as the r vector in this case, because we happen to put the origin of the coordinate system at the center of the circular motion. But remember, I listed out a bunch of what, comparisons of what these values mean. Remember that in general, the position vector and the r vector are different. The r vector always goes from the center of a circular motion. That p vector, if I had put the origin back here, then that would be different than r. But in this case, it's just 0, negative 0.40. And so now the velocity vector of that point P is equal to negative 2, 0, 0 plus negative 20, 0, 0 crossed with 0, negative 0.40. And that is negative 2, 0, and then 8. And that's meters per second. Well, I think maybe a better way to think of it is we're using we're calculating what the coordinate system sees, and then we have correction terms that go along with taking the time derivatives in a rotating coordinate system. And then, yeah, we're adding those two vectors together. But if we weren't doing the correction for the rotating coordinate system, and we were just trusting what our camera sees, we would have missed this whole, 008 part of the velocity. Which, in this case, intuitively, I think it's easier to do the velocity intuitively than the acceleration. What we're missing there is, I said it's, well, I didn't say velocity, but since this is away from the center of the circular motion, you have a velocity going this way because at that instant, this thing's whipping around like this. And the coordinate system doesn't see that. Yep. Yes. And if you look back one class or two classes or something, there's a list of comparing the watermelon equation to this new equation, and so it's listed in there. But R is a vector that goes from the center of a circular or spherical motion to the point you care about. P goes from the origin of the coordinate system to the point you care about. It's a position vector, and that's what a position vector is. But R always goes from the center of a motion to the thing. Okay, so now acceleration. So the acceleration of this point P is equal to the acceleration that the coordinate system sees plus time derivative of the angular velocity of the coordinate system crossed with the position vector plus 2 times the angular velocity of the coordinate system crossed with the observed velocity vector plus the angular velocity of the coordinate system crossed with the quantity big omega cross p. And then you can also do this as the second derivative of the position vector components. And this is the first derivative with respect to time of the position vector components. But this is the one that's useful to us in this case. All right, so let's just go through one by one, figure out what these values are. So first, the acceleration of p that's observed in the coordinate system. For that, we're imagining that this part of the shaft is not rotating, and we're just looking at the rotation of p around there. So what's the equation we'll use for the acceleration of that point p? Watermelon, yep. And so this is going to be alpha cross r plus omega cross quantity omega cross r. What's alpha? 0, 0, negative 15, that's right. R we had to figure out for the observed velocity before, so that's 0, negative 0.40. Omega, the lowercase omega is 0, 0, negative 5. Crossed with the quantity 0, 0, negative 5 cross 0, negative 0.40.
Yeah, you gave it as a positive value, so.
But I showed the direction of the.
Yeah, but
It's the same. It's according to the right-hand rule. So if my thumb was going in the positive z direction, my fingers would be going the opposite of the direction that's shown. So to get that direction, my thumb has to be going in the negative z direction. It can be going this way, and the angular acceleration can be the opposite direction. Then it would be slowing down. One arrow for both. Yeah, that's right.
Cranking up.
Yeah, if they're the same direction, it's speeding up. So what do we have here? So that is negative 2, negative 10, and this one is negative 6. So I think this is negative 6, negative 10, 0. Okay, so that's the observed acceleration. So negative, and then negative, positive. I think you're right. Okay, so we got this, and now we're just going down the list, element by element, to figure out what these values are. What's capital omega dot? 0. What's the position vector? Yep. Something about the position vector. Is that position vector an observed position vector, or is it a true position vector, or what? Like with the velocity and the acceleration, I was careful to make a distinction between those, right? What about the position vector? It's both. And that's because there's no time derivatives needed to express that position vector. And so one is the same as the other one, whether you're talking about it in a rotating coordinate system or a inertial coordinate system. What do we need next? Capital omega. What's that? Negative 20, 0, 0. And the last thing we need is the observed velocity vector. That's what we calculated before. Negative 2, 0, 0. That's the true velocity vector, but we want the observed velocity vector. And so now we can put this together. The acceleration of the point P is equal to this observed acceleration, negative 6, positive 10, 0, plus omega dot cross position vector. Omega dot is 0, so that has to be 0. Plus 2 times the vector negative 20, 0, 0, crossed with the observed velocity vector. That's negative 2, 0, 0. Plus capital omega crossed with the quantity capital omega cross P, so 0, negative 0.40. The third term goes away because if you take a cross product of two parallel vectors, it's 0. And so we get negative 6, 10, 0 plus this crossed with 8 in the z direction. And so that's negative 6, 10, 0 plus positive 160 for y. And so the total acceleration is negative 6, 170, 0 meters per second squared. Yeah. And so with some of these, you can sort of think about it and wrap your head around it. It's in the y direction. Also, you can see what the, where that comes from, what the term is. So that big acceleration in the positive y direction comes from the fact that this is a really high angular velocity, and you have a radius of 0.4, and so there's a big centripetal acceleration happening. And that's if you look back at how I listed out the terms in this equation, that's the unobserved centripetal acceleration. Someone sitting here moving with the coordinate system doesn't see that because according to them, this isn't moving, but still it has to be in there.
And so for more complex structures like that, let's say if there was another rotation between the horse and the wall, we would just go from...
Yeah, that's perfect. Yep. You're exactly right about that. I mean, we could have this thing, this could be a hinge and it's swinging this way, and you just bootstrap your way up piece by piece,
Do you go from the end on the right to the wall or from the wall to the right? What is the horse riding?
Yeah, it's a bigger horse. It's just bigger and bigger horses on top of another horse. Yeah. So you would go, so if this was on a hinge, you'd first want to calculate the acceleration of like this point, and so you'd start by putting your coordinate system fixed to this arm that's rotating this way and calculate the motion of this point. You get an acceleration there. And once you have that acceleration, then you can move up. So yeah, I guess you'd start with the thing that's fixed to the ground and keep moving towards more dependent things. You can, but you don't have to. But if you move your origin, you have to remember that you're going to have to deal with translational acceleration of the origin if you move it. If you keep it at the same location and just have it follow the rotations, then you don't have to use relative motion. But that's kind of probably for now getting a little too much into the weeds, but I think that's the kind of stuff that'll seem more clear once the simple stuff starts to solidify a little bit. Yeah. Okay, so let's do another one. Why not? Oh, C was calculate the net force. Thank you. And so Newton's second law just says F net is equal to the mass times the acceleration vector. And so I said the mass of the particle is 0.1 kilograms. Now we know that the true acceleration is -6, 170, 0. And so at that instant, the net force acting on that particle is -0.6, +17, 0 newtons. Okay, so now for this one, let's say that the wall's over here, and there's a member attached to the wall by a pin joint. And then at the end of this, another member rotates around a pin. And let's say we don't have a ton of time, so let's say that both of these are moving with constant velocities. Let's say this is 10 radians per second. Let's say that this one is 20 radians per second. and the lengths are each 1 meter. The vertical member. Yes, that's right. So this thing is just spinning this way around that little pin. And by the way, that this 20 radians per second here is not a true angular velocity of this body. It would be like an observed angular velocity relative to this. So the true angular velocity of this body, it doesn't come into the calculations, but it would be, well, it would be you add up this vector to this vector. We haven't drawn what our coordinate system is yet. Okay, so let's first do it with a coordinate system here. This is the horse. This is the cowboy. And so that coordinate system is going to rotate with the horse. But the point of interest, let's do the end. So that's the acceleration we want. Yeah, that distance just goes to where the body is. Okay, so we're going to do this, and then next time we're going to repeat the same problem, but instead of having the coordinate system rotating with the horse and positioned here, we're going to move the origin to here. It's still going to be rotating with the horse, but now the origin would also be accelerating. So we'll have to use relative motion. If we do it right, they have to be the same answers. Okay. But for now, we'll just do this. So you can think, is the origin accelerating? No. Are the axes rotating? Yes. So we know that the acceleration of p is going to be the observed acceleration of p plus capital omega dot with the position vector plus 2 times the angular velocity of the coordinate system crossed with the observed velocity of p plus capital omega cross quantity capital omega cross p. All right, so I guess let's write down the easy ones first. What's the position vector of the point P? Yeah, -1, -1, 0, exactly. What's capital omega? Zero, zero, -10. Yep. Because of the cross product, x cross y has to be z, so positive z is that way. This is going in the opposite direction. So 0, 0, -10. What's capital omega dot? Yep. And now we have to come up with the observed velocity and observed acceleration. So how do we calculate the observed velocity? We don't even need relative motion on this because we're assuming that this force is stationary. So we're just watching this point. You know, we're a little far away from it, but we're just watching this point in circular motion around the x-axis. So this is going to be, lowercase omega cross r. What's lowercase omega? Negative 20, 0, 0. And what's r? Yep. So here's one where the position vector and the r vector are different. Our position vector was -1, -1, 0. But our r vector is from the center of the circular motion, which is here, to this. So that's just 0, -1, 0. And so the cross product is 0, 0, 20. Bless you. Okay, now how do we calculate the observed acceleration? Yep, watermelon equation. So this is equal to, alpha cross r plus lowercase omega cross quantity, lowercase omega cross r. This one goes away because there's no alpha. So the acceleration of p that's observed is -20, 0, 0, cross quantity, -20, 0, 0, cross r, 0, -1, 0.
So is the acceleration just crossed with omega again for velocity?
So that is, I guess that's always true if the motions are completely circular motions. We've already done that, so it's just going to be, positive 0, positive 400, 0. That makes sense because that's a centripetal acceleration, and at this instant, the centripetal acceleration is straight up. And now we can put this all together. So the total acceleration of p is 0, 400, 0. Plus omega dot cross p. That one goes away because there's no capital omega dot. Plus 2 times capital omega, 0, 0, -10. Crossed with the observed velocity vector, which is 0, 0, positive 20. Yep, again, but it doesn't always. Plus 0, 0, -10. Crossed with the quantity 0, 0, -10. Crossed with the position vector, -1, -1, 0. That's 0, 400, 0, plus 0, 0, -10, crossed with -10, +10, 0, and so that is +100, +100, 0. So 100x, 500y, 0z meters per second squared.